In this video, I want to talk about how simple two-gene regulatory network can be compactly represented using vectors. So we have a simple gene network, X activates Y, and this can be represented by this discrete time equation. Y of I is P sub xy times x of I minus 1 plus py times y of I minus 1. So in case x and y protein concentrations are measured every minute, this equation is telling us that the current protein concentration is determined by x protein concentration 1 minute ago and also y protein concentration 1 minute ago. But how about if current y protein concentration depends on X protein concentration 3 minutes ago? So this is the term that we need, X of I minus 3. So in this regard, we want to have a general representation of simple two-gene regulatory network like this. Y of I is A sub 0 X of I plus A sub 1 X I minus 1 plus A2 times X I minus 2 up to A sub m x I minus m plus b1 y I minus 1 plus b2 times y I minus 2 up to b sub uppercase n times y I minus uppercase n plus some constant c. Now we see that this term corresponds to this term here. So A sub 1 is equivalent to P sub xy, and this term corresponds to this term. So B sub 1 is equal to P sub y. If all other parameters, A sub 0, A sub 2, up to A sub m, and B sub 2 up to B sub n, if all these parameters are zeros, then this equation becomes same as this equation. So you see that this is very general expression for simple two-gene regulatory network. Now, I want to compactly represent this general equation using vectors. This equation for y of I consists of many terms, and each term has two components. One is parameter, and the other one is a data component, which represents x or y protein concentration. A vector, W, includes all these parameter values, including this c. So this will be A sub 0, A sub 1, up to A sub m, also B1 up to B sub n, and this parameter C. By the way, this parameter C represents component that contributes to y of I independent of all these x and y values shown on the right side. This is parameter vector W, and we want to represent a vector as a column vector. We want to put transpose sign here. So this is basically a row vector. And if you put the transpose sign like this, then we have a column vector, something like this. So now we want to have all these data terms put together into a single vector called vector T. So this is data vector. It has x of I, x of I minus 1 up to x of I minus m, and y I minus 1 up to y of I minus n, and lastly number 1, because this 1 is multiplied by c. By the way, this m and n are positive integer, and we also want to put transpose sign here so that this t vector becomes a column vector. This must be T of I. And now y of I can be expressed as T of I transpose W. And this is basically dot product. We are multiplying row by column, which results in a scalar value, single value, which is y of I. T vector is column vector. By having this transpose, this term is a row vector, and this vector W is a column vector. So we are basically doing this dot product, and our result is y of y, which is a scalar value. Let's say you have a row vector A, which is 1 and 2, and B, which is a column vector, let's say 2 and 3. If you have a dot product, A times B, you will have something like this, 1, 2, and 2, 3 here. And you multiply this by this, and you get 2. Then you multiply this by this, and you get 6. And the answer is 8. Basically, you need to multiply the first component of the row by the first component of the column, and the second component of the row by the second component of the column, and so on. If you do this multiplication, you're multiplying the first component of data vector t of I, which is x of I, by the first component of the perimeter vector w, which is a sub 0, and you get this first term, a sub 0 times x of I. And if you multiply the second component of this data vector xi minus 1 by the second component of this w vector a sub 1, you get this second term, which is a sub 1 times x of I minus 1, and so on.